Hello everyone, today we'll talk about the solution of the problem find building where Alice and Bob can meet. In problems like this, where you have some array and you have some queries about that array and you have to answer all of those queries, so return an array of answers, a good starting point, if you don't know where to begin, is to think about if your solution is going to be online or offline. For those who are unfamiliar, an online solution will just go through all the queries and answer every query one by one. It'll answer query I before looking at query I plus 1. And that might seem very intuitive if you're unfamiliar with the concept. What's the difference between online and offline? Well, an offline algorithm has a wider space of possibilities. It can answer queries online. It can answer queries in a different order, which is what we are going to be doing now in this solution. It can also, essentially, which is connected to answering queries in a specific order, it can maintain a state of operations and just update that state, calculate some things, and along the way answer appropriate queries. In this case, we are going to be essentially solving this problem where it's going to be offline with respect to queries, but in a sense, after some pre-processing, it's going to be online with respect to heights. That's not the classic use of the term online, but it's, I think, a good way of thinking about it so that you can come up with that algorithm when you see a similar problem in the future. So you pre-calculate something about all the queries. In this case, we're going to be ordering them because we are going to be going over all the heights one by one and essentially online answering the question based on them. We're going to be going over all the heights, and for every query for which this height is the answer, we're going to be finding that out when we are looking at this height. Immediately we're going to be answering all the queries for which this is the answer. And to make sure that we can do it, we have to make sure that the queries that we're looking at, both buildings in those queries, have their indices not to the right of the index of the building that we're looking at. So we're going to have to order them based on the rightmost of the two indices. So the maximum of queries is just the maximum index of a building, of those two buildings. And we'll want to sort queries based on that, and we want to use an indirect sort. So we generate a list of all the indices from 0 to n-1. This is our order, and we sort our order. That's because we want to generate the answers for all the results. So we have to maintain the original order, but go over queries in the sorted order. So we sort them based on increasing max of the two values. Because we're going to be going through all the heights, enumerating them, and only looking at queries for which our current building could possibly be the answer because it's not to the left of the two buildings within the query. Now we're going to be putting some answers in our list of answers, and there are some edge cases in this problem where it's the easiest probably to think of them and calculate them beforehand instead of trying to change the core algorithm. Those edge cases are, for our query, if Alice and Bob start at the same building, they don't have to move at all, they can just meet at that building. We don't have anything to do. And this is a case where their heights of the two buildings is the same because it's the same building. If the two buildings are different and their heights are different, and moreover, the left building is smaller than the right building, so min of query is the smaller index, max of query is the higher index of a building. So if the building to the left is smaller than the building to the right, the answer is certainly the building to the right. Because the person in the bigger building doesn't have to move at all. The person in the smaller building can move into their building because their building original is smaller. And it's impossible to get anything better because the answer has to be at least max of query. Otherwise, we'll calculate the answer later. So we put the placeholder -1. And this will make it easier for us to actually run the algorithm. And the algorithm will be going one by one over all the heights. And when there is, we can imagine, a set of queries for which we don't know yet the answer, but we know that the answer can be generated by some building that we see. So those queries that all the buildings of that query were already seen, but we still don't have an answer. If we have that set, then our current building that we're looking at can be the answer to some of those queries. And what queries are those? Well, it certainly is the answer for all of those queries where both the buildings in that query are smaller than the height of the current building, right? So if we know that there is a query, let's say, about the building 0 and building 2, we're currently looking at building 4, and both building 0 and building 2 are smaller than building 4, then if we still haven't had the answer for the query 0, 2, then 4 is that answer, and we can remove that query. So if we can maintain that set of queries, essentially sorted by starting from the smallest height of the higher building, then our building will be the answer to some prefix, maybe empty, of those sorted list of queries. And instead of keeping the sorted list, since we're only at every step interested in the query that has the smaller building, we can just keep a priority queue, or a heap if you prefer. So we'll be going over all the order of queries with our pointer q. We have our priority queue, which at first is empty. This is all the queries where both buildings have already been seen, which means that we can have the answer for that query. And now, whenever we take a new building, then all the queries that end at that building can be added to our priority queue. So while there are some remaining queries, and max of that queries is less than or equal to I, which means that those two buildings are to the left of their current position, we can add them to the queue. And of course, we only want to add them to the queue if the result is -1. Otherwise, it's one of the special cases we already know the result. So if we don't know the result, we take that query and we push it into our priority queue using heap queue heap push, and later, of course, heap queue heap pop, because that's how you operate on heaps in Python. And what we keep on our queue is a pair of the max height of the building, and this we want always to look at the smallest of all the possible queries, the smallest, highest building, and of course the index for us to later update the result array. Q plus equals 1 for every case where we enter this loop, because we want to move forward since we've processed one more query. And now, while there are some queries waiting to be processed, we look at the top query. In a heap, pq of 0 is the element that's the smallest. pq of 0 is the height of the higher of the two buildings, and if they are smaller than our current building, then we can move both of them to our current building. Since they are at the priority queue, we still don't know the answer, so the answer is our current building. So we take the index, this is the second value, so pq of 0 of 1, or we can just heap pop and unpack it into this index. The result for that index is our current value I, and at the end we return the result. So this is a pretty nice idea. The algorithm is actually quite simple. Just maintain all the queries for which we can know the answer, go through all the possible buildings which can be the answer, and write down where they are an answer. And it's very easy to tell because they are an answer for everything where the highest building is smaller than the height of the current building that we're looking at. The edge cases that I mentioned, for instance, is that here we have less than, and theoretically we could have less than or equal, but that would not work in the case where both the buildings in the original query are of the same height but are not the same building. So if we have a query about a building of height 2 and another building of height 2, then we cannot meet at the right of those two buildings. We have to meet to the right of both of them, because the left 2 cannot move into the right 2, because the movement is only possible if there is a strictly less than and not less than or equal. So this is, for instance, a case where this condition is much simpler because we have these special cases covered here.